Hello everybody and welcome back to the channel. Today we'll be racing against my bowels because I have about 15 minutes until I have explosive diarrhea. So let's get this video underway. Today I will be doing the low-level design of an order book. If you don't know what an order book is, I'm going to teach you. And on the event that this happens to turn you into a Jordan Belfort type, please do send some hook on my way. I'll greatly appreciate it, and for legal reasons that was a joke. Okay, let's get into this. Alrighty, so let's go over what a limit order book is. We'll go over some design decisions that we might make when implementing this. It is more of an algorithmic problem, maybe more than anything, but I don't really think there are too many good videos actually covering how to do kind of the class design that you would want for an order book. And so I'm going to try and go into that and explore it with a little bit of depth. Okay, so what is a limit order book? Well, let's imagine that we're only considering one stock for now, because in reality there's going to be different order books for every single stock. But the general gist of this is that an order book basically keeps track of all the open orders. When you're trying to buy or sell a stock, sometimes there's not somebody else who wants to buy or sell that stock and take the other side of the trade. When that happens, your basically unfilled order goes into the order book. And there are two sides of the order book. There's the ask side and the bid side. The ask side basically represents all of the open selling orders, meaning let's say I had 100 shares of an Apple stock and I wanted to sell them. That would go in the ask side of the order book until that half of the order was filled. And then same with bidding. Let's say I wanted to buy 50 shares of Google. Well, then that would go in basically the bid side of the book until someone else basically went ahead and sold me 50 shares. So like I've said on the slide here, we have basically the prices and the corresponding volumes, which is just the number of shares, that people who have not yet had their order filled want to buy and sell of a stock. And there are a few rules to this order book basically for, when new potential trades are coming in, how they would actually go ahead and get filled. So as you can see, we have our basically bid and ask side of the book, and a trade is going to be made if the highest bid is greater than or equal to the lowest ask, meaning that the spread has been crossed. So the spread is basically the term for the difference between the lowest ask and the highest bid. And so when they cross, it means that there's someone who's actually willing to pay greater than or equal to the amount that someone is willing to sell at. And so a trade is going to be initiated, and that volume is going to be removed from the order book. Now, what if it's the case that one side was in the order book already and the other side basically initiates the trade? Well, the price that order is going to basically happen at is the price of the order that was already in the book. So keep that in mind. That's one rule we have to talk about. Another one is actually going to be the fact that basically if orders are all going to be, basically if an order comes in that crosses the spread and there are multiple orders on the other side, or there are multiple basically open orders on the other side that could fill an order with that, you're going to ultimately perform the trade with the open order that came in first. So we're going to be doing those in chronological order. It implies we'll have to be using some sort of queue or something along those lines down the line based on a timestamp. Okay, so let's move onwards. You can read the slide for more details about the rules, but I hope that explains things. Okay, so let's think about our order book interface. So we'll first do a basic order book, and then towards the end of the video I'll explain some possible expansions to the problem and touch upon those a little bit, but this is going to be our main functionality that we care about the most. So the interface that I want to define, and the reason I'm doing this as an interface is because there are multiple possible implementations of our order book, is going to have three main methods. We have one to place an order, and so placing an order is basically going to do the following. It's going to try and fill that order, meaning it's going to try and find an open order in the order book that can be combined with it to make a trade, or if you can't make a series of trades due to that order that was just placed, then you're going to go ahead and place that in the order book, and maybe down the line that trade will actually go down. We also have this option to cancel an order. Like I said, sometimes orders are going to be placed but not actually filled, and they'll go in the open order book. Canceling that order will make sure that you won't actually be able to fill that order in the future if it has yet to be filled. If it has been filled, that's just a no-op. And then finally, we also want to be able to get the volume at a price point for a given side of the trade. So let's say I want to see, all right, how many people are currently selling the stock Apple for $50? Or not how many people, but rather how many shares are being sold at the price of $50. We could then go ahead and easily get this by calling our get volume at price method. Okay, so let's also, obviously, we need to basically encapsulate the state of an actual order. And so I went ahead and listed out some fields that would be useful in something like an order class. Having an order class is useful for a variety of reasons. Technically, the state isn't going to be changing too much, so it's possible that we don't need a class. We could maybe use some different data structure like a dictionary to represent this. But at the end of the day, being able to kind of abstract this away in a class is good for, putting it in other data structures. For example, something like a queue or a linked list or a heap or anything along those lines. It's nice to have kind of a node structure that we can abstract an order away with. So we're going to have an order ID, we're going to have a timestamp, we're going to have a side that is part of our buy or sell enum, so I'm just going to assume side is buy or sell. We're also going to have a price, which is going to be a double or a float. We will have a volume, which is the number of shares that's either being sold or bought, and then also a client name. That's just going to be useful for when we're actually printing out a trade that has executed. And again, obviously I've made these all private, so I'm assuming that in an actual class you would have public getters and setters, just for the purposes of kind of making sure that you can't actually access the instance variables of this class. Okay, so let's go ahead and think about some sort of data structures for our limit order book, because this is ultimately going to be a pretty complex problem, and there's not only one way that you can do this, but I'm going to touch upon one possible implementation. And if you guys have any other ideas in the comments, feel free to go ahead and comment those. I'd be interested to see what you guys can come up with as well. But as far as I'm aware, this is one of the more common ways of implementing it. So basically, we know when an order comes in, let's imagine that we're submitting a buy order, right? So I want to buy 50 shares of Google. The first thing that we're going to do is go ahead and look at the lowest price of the sell side of the limit book, right? Because I want to see what people are willing to sell Google for. If I'm willing to buy Google shares at a price that's greater than or equal to that lowest sell price, then we're going to execute a trade. And if I wasn't able to buy all the shares that I wanted, I'm going to keep checking the sell limit order book in order of the lowest prices to see if I can make even more trades. So obviously we're going to have some sort of while loop in our logic. And keep in mind as well that I basically just told you guys the way that I'm looking at the limit order book in terms of who I'm going to actually execute my trade with is in terms of the price point, right? I am prioritizing open orders that have the lowest price. So what would be really good for this would be a priority queue, which is often implemented by a min heap. So it would be really useful to kind of represent the sell side of the order book with a min heap, so that way I can quickly see what's the lowest price that I can buy shares at. And similarly, you can also implement the buy side of the order book with a max heap, so that you can quickly see what is the highest price that someone's willing to buy shares of a stock at. And so now we basically have this structure of two heaps. We have a min heap for our sell side, we have a max heap for our buy side. And in addition, it actually gets a little bit more complicated. But keep in mind, and sorry, there's a typo on the slide, I said n log n inserts and pops. It's actually log n, where n is the number of nodes in the heap. But what actually are our nodes in the heap? It's not actually going to be so simple as to just say that, hey, we have just a bunch of order nodes in our heaps, right? Because we actually said to ourselves, hey, we know that we basically have all these orders, but there can be many orders at the same price point, right? I might want to buy 50 shares of Apple, and then, my friend also might want to buy 50 shares of Apple. And so we would go in the heap in the same place. But I've already said that, if there are two people willing to buy shares at the same price, the one who gets priority is the one that actually submitted their order earlier, meaning they have an earlier timestamp. So what we could actually do, we have a couple options here. One option is to just go ahead and make our heaps based on both the price and the timestamp, but it is actually a little bit algorithmically faster if we were to use a queue. The reasoning for this being that now we're not adding a bunch of extra nodes to our heap, which goes around in kind of logarithmic time, but rather we can have basically a heap of queues where the queues are representing just one price level for an open order, and then within those queues we have actually basically the order nodes themselves in the order that they were submitted, right? So it means that pulling from the beginning of the queue is going to show you the earliest order, and then we're going to get the things that we want, right? So now we finally satisfied our requirement of being able to look through those heaps in the proper order, and also if there's a tiebreaker, we can settle it using that timestamp field. Okay, so now we have basically these two heaps, right? We have our max heap and our min heap, and each of those heaps is made up of a bunch of different queues, and those queues contain orders, right? So this is already getting pretty complicated. And I understand that, and I empathize with you there, but it's only getting worse, because we mentioned that we need volume. So volume is basically saying, what is the open amount of shares that people either want to buy or want to sell at a given price. And so right now we know that all of the orders at a given price are represented by basically being part of a queue. And that's all good and well. However, it's not very efficient time-wise. And we know that we want to make our algorithmic complexity as low as possible during the course of this problem, because in an actual market exchange or a stock exchange, it's super important to make things super fast, or else there are going to be inefficiencies that people can take advantage of. So we want our volume to basically be running as fast as possible, and right now our volume, or at least calculating it, would be an O of n. The reason for this being that we have to iterate through a queue at a given price point and add up the sums of the number of shares that each order wants. So instead what we can actually do is, as opposed to kind of lazily figuring out what the volume is, we can actually pre-compute it. And we can do this by maintaining a hash map. So the hash map is going to basically take in a tuple as a key, where the tuple is both the price that we care about and also the side, so buying or selling. And every single time that we add an order to our limit order book, we can go ahead and increment the volume available for that order's price inside in the hash map. And if we were to ever remove an order from the limit order book, because either it was filled or it was canceled, we can go ahead and remove the corresponding volume amount in our hash map. So that's just an extra thing to keep up with. Okay, next we have cancellations. Cancellations is probably where this problem gets, I would say, the most challenging in terms of actually going ahead and thinking through the trade-offs that we need to make. And there are a couple of possible ways that we can cancel an order. We can kind of actively do it, or we can lazily do it. So the active way that we can do this is we basically go ahead and take the node representing an order, and we simply remove it from the queue that it's a part of, and effectively remove it from the heap. So we're now no longer ever going to consider it for filling future orders. So this is really good in the sense that it means that there are going to potentially be fewer things in the heap, right? If we emptied an entire queue out because all of the nodes are canceled in it, now we can go ahead and remove that queue from our heap. And as a result, even though all the operations in the heap are log n is going to be smaller, so that is going to give us a time complexity advantage for future operations. But basically, by actively removing things from the heap, it also means that we're incurring extra time complexity whenever we do a cancellation. So the first thing is that we're going to be removing a node from a queue, right? Because we have a heap of queues of order objects. And so we're removing an order object from that queue. We know that removing arbitrary nodes from queues is actually an O of n time complexity. However, there are optimizations that we can make in order to improve this. For example, instead of just using a queue with a linked list implementation, we can implement our queue via a doubly linked list with a hash map, which I've covered plenty in prior videos. And by doing so, we can basically use our hash map in order to get the location of the node and then remove it in O of 1 time. So that does save some time complexity there, but it still doesn't stop the fact that if we ultimately have to remove the corresponding queue from the heap because, you know, there's no more order objects in that queue, meaning all the orders at that price point are no longer available, now we have to remove that queue from the heap, and that is going to be a log n removal, assuming that we know the location of the queue in the heap, which is only going to happen if we have a hash map pointing to it. So again, this is, you know, getting very algorithmically complex at this point. The other option that we actually have allows us to not remove anything from the heap unless it's actually going to be popped from the top of it. This is because we could lazily mark orders as canceled by basically just setting a field in them called canceled, and then as we run through our queues during our while loop, as we check for orders to potentially fill, if we see that an order is marked as canceled, we just go ahead and skip over it. So this does have some time complexity advantages in the sense that we'll never have to remove anything from the middle of the heap, but it also does mean that if there's a lot of cancellations, we may just constantly be popping nodes from the heap, taking a good look at them, and saying, actually, you know what, we no longer want to consider you anymore, now we just have to move on. So we're going to add time complexity there, and in addition, by not actively removing empty queues from our heap, we're also going to have more nodes in the heap, and again, like I said before, even though the time complexity of a heap is always O of log n is going to be larger because there may be some empty queues in there. Okay, let's go ahead and put this all together. So I'm actually going to go ahead and implement everything that I've just spoken about so that I can materialize it for you guys and it makes a little bit more sense. And additionally, one of the things that I want to do is kind of do the active cancellation method, not the lazy one, so you guys can see how that would work in reality. So let's go through the fields of the order book itself, and we can go ahead and work out what we have. So we have our min heap for the best ask part of the order book. We've got our max heap for the best bid part of the order book. We have a hash map from order ID to order, and that's I'm going to call order map. It's going to allow us to cancel orders pretty easily. We also have a volume map, which, like I said before, is keyed by basically a price and a side. And then we also have a queue map, which is basically saying find the corresponding queue that's part of a heap as keyed by price and side yet again. And that's going to allow us to easily remove queues from a heap in log n time as opposed to linear time. Okay, so we've got our place order method. So the first thing we're going to do is figure out what the opposite side of the book is. So if I'm buying, the opposite book would be sell. And if I'm selling, the opposite side of the book would be buying. I'm doing the same thing for the same side of the book. And then I'm also placing our new order that's going to be placed in our order map. Okay, now this is kind of the crux of everything. We're going through our while loop and basically filling it as long as there's volume in our order. We're saying while there is order volume, while the opposite book isn't empty, and while the first order to be filled in the opposite book, aka the one with the best price for us, has volume, we're going to go ahead and actually figure out the other order, which is just going to be at the top of the other heap. We're going to figure out the trade price, which I basically said is going to be the price of the other order that is already in the book. The volume is going to be the minimum of volume between our order and the one already in the book. And then we can go ahead and print and basically say, here's a trade that's happening. And we're going to have to adjust both our order's volume and the other order's volume by subtracting the amount of the trade volume. Then finally, the last piece of the puzzle is basically saying if the other order no longer has volume left, we can remove it from our book. And we can do that by calling the cancel method. I'll go into the cancel method in a little bit because we've extracted it away for now. But it's effectively just going to remove the other order from the limit order book. And then finally, if we've gone through our while loop, we filled every single order that we can as part of the one that was just placed, and there's still volume left to be filled, so let's say I wanted 50 shares of Google and I was able to buy 45, but now there's 5 left. I'm going to go ahead and put those 5 left into the order book, and I'll go ahead and show that helper method in a second. Okay, so we've got add order to book, where I'm basically saying which half of the book that I'm putting it in, and I'm also giving myself the order node here. So now all I'm going to do is say, okay, if there's no price queue that basically corresponds to what the order should be going in, we have to create that price queue. And once we've created that price queue and it exists, we should go ahead and put the order in the price queue, and then furthermore, increment the actual corresponding volume of the price and side corresponding to the order. So easy enough, fine, add order to book, sure, just a helper method. And then now we actually have cancel order because we used this before, so let's go ahead and do it again. All the cancel order is basically saying is we look for the order ID in our order map, which would indicate that the node has yet to be canceled, so it's probably somewhere in the order book, and it hasn't been filled either. And basically now all that we're going to do is go ahead and say, okay, we're going to go in the order map, we are going to look at our price queue that this node should be a part of. We're going to remove the order, which we got from our hash map. So this is going to be an O of one time because I'm assuming that price queue is a doubly linked list. And then finally, we're going to say if the price queue that this order was now a part of is now empty, we need to go ahead and remove that price queue from the heap. This is going to be that log n removal. I keep writing n log n, but that is a typo. And then finally, we can go ahead and remove the volume of this order from the order map that's corresponding to it, and also delete the order from the order map as well. So again, yeah, we're just subtracting the volume, deleting the order from the order map. Simple enough. We're basically just undoing everything that we did when adding an order. The last piece of the puzzle is getting the volume at a specific price, where all we're literally going to do is call volume map because we already have this kind of listed out for ourselves, which is really great. So we return volume map with a given price on the side, and we'll get the corresponding volume. And if it's not in the hash map already, we're going to return 0. There's nothing in there. Easy enough. Whew! Okay, moving on. Let's go to extensions to the problem. I know this is going for a while, and I really have to poop, but whatever. Basically, let's imagine that no longer do we have limit orders, but now we have something called market orders. Market orders are basically saying, okay, we're no longer specifying a specific price that we want to buy at, but we're actually just specifying a volume. And so you're going to go ahead and fill as many shares of the volume as you can, and then if there are still shares remaining left over, don't put any order in the order book, just get rid of it. So this is pretty simple, and we would actually do something similar to the limit order. We're basically just going to continue to run through the heaps as normal, right? So if I'm trying to buy and I say, let me buy 20 shares, I don't care what price they're at, I'm going to start from the bottom of the sell order book, aka the lowest price that people are willing to sell at, and I'm just going to keep filling those orders as much as possible until I have gotten all of my 20 shares. Okay, what is another extension to the problem that I've seen? I've also seen trigger orders. Trigger orders are similar to limit orders, but basically you set a price, and then the second that the book basically crosses that price, the second the spread or there's a transaction that is basically beyond that price, now the trigger order is going to basically place a given order as specified by the trigger. And trigger orders can even trigger other trigger orders. So basically all that happens is you're running through your algorithm as normal, but every single time an order is a trade is executed, you can basically have separate heaps that correspond to basically the lowest sell trigger order and the highest buy trigger order. And then you can basically check them that way, and once a trigger order is triggered, you can put it in a queue of trigger orders to run through, and then you can start executing all of the trigger orders in a queue before you place any new orders or accept any new orders to be placed. Annoying, I know. If you guys want me to go into more depth in this in the comments, I'm happy to do so, but I don't really think it's a main part of the video here. Alright guys, well done. This was a lot, I know, but again, if you're feeling particularly generous, I'm feeling particularly accepting. So yeah. Alright guys, well I hope you appreciated the video. Like I said, this is a problem that I don't really think there's that good of like a posted solution online for this. Plus, in addition, it is something that definitely has come up in interviews that I've done in the past, and so yeah, I'd recommend learning this one up, especially if you're planning on applying to any finance companies. But yeah, best of luck guys.